Okay, so the last third of this unit has to do with gravitation. Okay, the unit's name is circular motion and gravitation. So this last bit of the unit is about celestial motion, gravitation, satellites, okay, that kind of thing. How does gravity, acting as a centripetal force, make things work the way we know they work? Okay? Everybody all right with that idea? All right. So believe it or not, even though this whole second half is supposed to be about gravitation, the first thing we're going to go over is all the discoveries made before we understood how gravity actually worked. Okay, it's actually kind of unbelievable that people figured out how the planets and things like that in the heavens move without an understanding of gravity acting as a centripetal force. Okay? So, first thing we're going to cover is the greatest feud in science history. Okay, like this makes the Hatfields and the McCoys and the Montagues and the Capulets look like small fry. Okay? The two people we're going to talk about today hated each other. Okay? Not that that's a good thing, it's not. Okay? But it makes for good drama. Okay? In fact, one of them went to his grave like swearing like death on the other guy. Okay? Like that's how much they hated each other. All right? So the two people we're going to talk about here are Johannes Kepler and Tycho Brahe. Okay? Tycho Brahe was an astronomer, not a physicist. And he was also not really a mathematician. He spent his whole life being up at night and asleep in the day and studying the movement of the stars in the heavens. That was his whole life. Okay? He spent his whole life documenting the position of the planets you could see without a telescope, okay, moving through the heavens. Tycho Brahe was also of the terra-centric mentality. That means Earth is at the center of the universe, and everything orbits the Earth. Okay? Tycho Brahe's problem was he was really good at making observations about where planets were at various points in time. So good, in fact, that his data didn't seem to support the idea that the Earth was at the center of the universe. This is where he ceased to be a good scientist. Rather than accept what his data was saying, he just assumed, I'm not good enough at math to make this work. It must be more complex than I think it is, because I know that the Earth is at the center of the universe, even though my data says otherwise. So he said, I must be misinterpreting it. I'm going to hire a mathematician to prove it. So he hired Johannes Kepler, who was an amazing mathematician. Okay, had a very long resume about all the wonderful math that he had done. Okay, and he also had a pretty good understanding of physics and celestial motion, perfect for the job. Well, Tycho Brahe handed over his life's work to Johannes Kepler. He said, here's my life's work. Make it say that the Earth is at the center of the universe. Here you go. Okay? So Kepler, not really having a feeling on whether the Earth was the center of the universe or not either way, okay, said, okay, I'll have a look at your data. Well, here was one of the things that Tycho Brahe had in his data that he couldn't explain. Mars in particular gave him a lot of problems. He observed as Mars moved through the sky, it followed a nice orbit, like an ellipse or a circle. Okay? But sometimes Mars would appear to stop in the sky and move backwards, and then stop and go forwards again. Okay? That's pretty hard to explain if Mars is orbiting the Earth. Why would a planet just stop, back up, and then turn around and go back the other way again? Pretty hard to explain that from an orbital mechanics perspective. Okay? He just figured, I can't do the math. It must be more complex. I mean, if you look at some of the terracentric models that people made up for how everything moved in the heavens to explain Earth being at the middle, they're beyond ridiculous. Okay? It's so much easier to just say everything orbits, the sun, and then from there. Okay? So, why do you suppose Mars does this? Because it does. In the sky, that's what it looks like. Why does it look that way? Because obviously Mars does not stop, back up, stop, and go forward. Okay, let me pose something you have more experience with. You're on the highway, and you're traveling faster than a car in the distance. Okay? As you approach that car, what direction does that car look like it's going? Like as you pass it, that car appears to go backwards. It appears to fall behind you because your relative velocity is greater than its. Its relative velocity to you is negative. Okay? That's why it falls behind you. But eventually you get far enough past it that you can tell it's still moving forwards. Well, this is exactly what happens when Earth passes Mars in its orbit. Earth is inside of Mars. So it orbits more quickly. The period of its orbit is less. Okay? So as it passes Mars in its orbit, Mars appears to go backwards in the sky for a little while until we're far enough ahead of it that it appears to be following us again. Okay? That's what Tycho Brahe observed time and time again over his, well, very long career as an astronomer. He also observed the same thing going on with the outer planets. Okay? It wasn't as obvious because he didn't get to observe them as often, obviously, when it takes 12 or 20 or 80 years to orbit the sun, you might only get one look at it. Okay? So Mars was the one that he saw this with the most often. Okay? So he handed that over to Kepler, and Kepler starts doing the math. Kepler likes having a job. I mean, you can understand why. It helps you feed your family and important things like that. It doesn't take him very long to go, oh boy, he is not going to like what I have to tell him. He believes with every fiber of his being that Earth is at the center of the universe, and his data, which is immaculate, does not say that. And there's no way for me to make the math work for that. So he digs in his heels, he kind of drags his butt a little bit, and tries to drag this job on for a while. Finally, Tycho Brahe gets tired of it and he's like, look, you're supposed to be good at math. You should have this done by now. And Kepler's like, yeah, about that. I'm done, and you're not going to like it. And when he told him what he discovered and showed him the math of it, Tycho Brahe fired him on the spot and blew up at him and tried to discredit him in the mathematical and scientific communities. That's not really fair to Kepler, and Kepler knew that. So he took Tycho Brahe's life's work and used it to humiliate him. You can imagine why people would be bitter. Okay? There'd be some hard feelings, okay, in this situation. You fired me for doing my job. You didn't like what I did, but I was right. So guess what? Hey, everybody, look at what this idiot thinks. Okay, for the rest of his life. Okay, so Brahe went to his grave still believing the Earth was at the center of the universe, but his tombstone should say, I was wrong and can't admit it. Okay, because his data actually was used to prove that the sun is the center of the solar system. Okay, and then beyond that the sun orbits the center of the galaxy and so on and so on. Okay, so that was kind of a big deal. Now, to prove the math, Kepler took Tycho Brahe's data and came up with Kepler's laws. Okay? The laws that govern how the objects orbit the sun in our solar system. Okay? So, Brahe's data was so complete that he was actually able to show that when Mars and when Earth and all the planets orbit the sun, that their speeds change. Okay? Now, from what we know, okay, this Kepler didn't know. Okay? He didn't know about gravity being a centripetal force. Okay? But he did know this relationship. So if speed changed, that meant that some of these other variables also had to change. Not knowing so much about gravity per se, he correctly calculated that if something moves faster, it's because it's closer to the sun. So he said the orbits of these planets are not perfect circles. They're actually ellipses. So there are points in time where the Earth is closer to the sun than others. Same is true for all the planets. Okay? There are very few planets that actually have very close to circular orbits. Venus is probably the best one. Okay? But most of them, they're slightly elliptical. Okay? As you get further out, into the Kuiper belt, those objects become very elliptical. And they have actually highly squished orbits. All right? So he proved this idea. Okay? This is greatly exaggerated, by the way. If the Earth actually followed an orbit like this around the sun, we would fry and freeze, okay, consecutively. Okay? Earth's orbit is only a few % different at perigee, that would be the closest point, and apogee, that would be the furthest point. Okay? But it is elliptical, which means Earth is closer to the sun at some points of its orbit than others. Okay? Now, at this point, usually people are like, oh, that must be what causes the seasons. Is that true? It's absolutely not. We're actually closer in January. Okay? Perigee happens during our winter. Okay? What causes the seasons? A little bit of that and a little bit of this. The Earth is tilted at 23.5 degrees. Okay? So when we're here at perigee, the Earth is actually tilted like this. Okay, tilted away. The North Pole is tilted away from the sun, right? And then over here, okay, the North Pole is tilted towards the sun. Okay, and then at kind of this point and this point, okay, tilt's still the same, but now those are what days of the year? What day of the year is this? What day of the year is this? Oh, sorry, this would be September. Sorry, September 21st. Okay, and this would be March. Okay? Now, what do you notice though about, like, if the Earth is further away there in June, even though we're tilted towards and it's summer for us, it's moving slower. You ever notice that the seasons and the months are not all the same length? That used to bother me, okay? Because I can still never remember which months have 30 and which have 31, because it's dumb, right? But, okay, there's actually a reason for it, and it's because of this, okay? The months are different lengths because the seasons are different lengths. We move through this part of the orbit faster because we're closer to the sun. So we complete that part of the orbit more quickly, which is why February has to be so short. Okay? Winter is the shortest season because we're moving through that part of the orbit faster. Okay? Spring and summer are longer, okay? Because we're moving through this part of the orbit more and we're moving slower. Okay? This is all stuff that Tycho Brahe had recorded. Okay? All his data that was used to humiliate him, okay, was all perfectly recorded and perfectly explained by what Kepler calculated, that the Earth and all the planets actually move in orbits that are elliptical, ever so slightly, but elliptical. Okay? Now, at that point, oh sorry, this was what I was gonna, it's a better diagram. Anyway, okay, so the Earth's orbit is not perfectly circular. It's slightly squished, and believe it or not, that actually is slightly squished, but it looks almost perfectly circular because the difference is very small. Okay? Now, when Kepler came up with this idea, people are like, okay, planets' orbits are slightly elliptical, but can you prove it? Okay? They wanted to kind of see the math of it. Okay? So he came up with basically two laws. Okay? And those laws were the law of the law of elliptical orbits, okay, that first one, and then the law of equal areas, which was the math of sweeping out different amounts of the orbit, okay, in terms of area, okay, every time interval that was the same swept out an equal area. Even though the radius was shorter, okay, the arc was longer, right? So they would always have an equal area. So if we're looking at those seasons again, okay, winter is only 89 days out of 365 and a quarter. Okay, autumn is 90 days. Okay, spring is 93 days, and summer is 94 days for us in the northern hemisphere. The southern hemisphere obviously is reversed. Okay, but that's because the Earth's orbit is elliptical, and we're further away. We're at apogee, okay, during the summer months. Okay, so we cover less of that arc, the circumference of it. Okay, everybody all right with that? All right. Now, this number here, okay, is on your formula sheet under other useful constants. Okay? On there it is labeled average Earth-Sun distance. Okay? That is the average orbital radius of Earth. Okay? Obviously, since the Earth's orbit is an ellipse, it's not always that number. In fact, it's probably never that number. Okay? Or only that number for an instant, okay, during the orbit. But that's the average. So when we do our calculations, for our purposes, we treat the orbit to be a circle. Okay? Even though technically it's not. Okay, so Kepler's first law, that the orbits are ellipses, okay, easily provable. Then he came up with the second law, which is the law of equal areas. Okay, so he showed that if all of these represent the same amount of time, they all have the same area. Okay, the radius is different, okay, but then so is the circumference of the arc. Okay, but when you calculate the area, it's always the same. That kind of accounts for this idea that the speed of the orbiting body is changing because its radius is changing. Okay, so you have the law of elliptical orbits, and the law of equal areas was kind of the mathematical proof of that. Okay? Now, if we're looking here at this chart, okay, this chart shows the eccentricity, that is how elliptical is the orbit of each planet as kind of a percentage. So how much closer is it at perigee than apogee? All right. Mercury is quite elliptical, actually. Okay, it is 20.5% closer at apogee, or sorry, at perigee than it is at apogee. So that's quite a bit. Okay, its orbit is pretty elliptical. It gets a lot closer to the sun at that point than it does at the other. Okay, for Venus, it's almost perfect. Okay, it's less than 1% off of a perfect circle. Okay. Earth, 1.7% off of a perfect circle. Okay. So pretty close, but not perfect. Okay. Enough to cause, okay, those differences in the length of day. Okay. For Mars, it's actually fairly elliptical. And that's partly due to the gravitational influence of Jupiter, okay, pulling on it a little bit as well. Okay. But Mars seasons, the seasons on Mars, are actually quite a bit more exaggerated than our own. Okay. Ours are all within, a few days. Okay, but seasons on Mars can be weeks different in their length because Mars's orbit is 9.3% off of a perfect circle. Okay, Ceres, which is the largest asteroid in the asteroid belt, about 8%. Jupiter just under 5%. Saturn just over 5%. Okay, Uranus, by the way, that's how it's pronounced. Uranus is something else. Okay. Uranus is how that's pronounced. Okay, 4.7%. Okay, Neptune, pretty circular. Okay, and that's because there's not a lot of mass beyond it to influence its orbit. Okay, Pluto, on the other hand, holy smoke. Okay, it's way off. It's 25% closer at perigee than at apogee. In fact, Pluto's orbit is so elliptical that at times it is closer to the sun than Neptune is. Okay? It actually crosses Neptune's orbit. Okay? This is part of the reason why Pluto and all the stuff discovered beyond it are no longer considered to be true planets. Okay? You guys were too young to remember this, but it was a big deal when I was in university. They disqualified Pluto as a planet, kicked it out of the planet club. Okay? And so now it's just a Kuiper Belt object. Okay? For a couple of reasons. To be considered a planet, you have to lie in the elliptical plane, okay, or the plane of the ecliptic. Okay, so here's the sun. This is the plane of the ecliptic. The 8 planets lie along that plane, okay, essentially, which means they can eclipse each other. Right, so they lie within that plane. Pluto orbits like this. Okay? It does not lie within the ecliptic plane. It also goes inside of Neptune, so it doesn't dominate its orbit. Okay? A planet has to dominate its orbit, that is, clear out other things. This could collide with Neptune at some point, okay, and be dominated by Neptune. Okay? It will be destroyed or captured. Okay? So all the objects beyond Pluto, like Eris, okay, and Sedna, okay, those are 2 of the Kuiper Belt objects. Obviously, we found way more of those since New Horizons went past Pluto. Okay, there's tons and tons of other objects out there, okay, and their orbits are highly elliptical. Like if you look at Sedna, it's almost like a comet. Okay, comets come in kind of like this. Okay, they're way out here in like the Oort cloud. They come in and go like this around the sun, and then they go way back out, and that can take hundreds to thousands of years. depending on where they are. Okay? Those are highly elliptical orbits. Okay? And of course, they cross the orbits of other planets, which can be problematic. Okay, so if we're looking at what that means for the Earth, okay, when the Earth is at perigee, it moves at 109,289 kilometers an hour. Okay, we're zipping through space. Okay, when it's at apogee, it's 4,000 kilometers an hour slower. Okay, significant. Okay, which is why summer is longer. Nice for us. All right. Now, the last law is the law of periods. Okay? This was an additional mathematical proof that everything orbited the sun in our solar system. Okay? And it was the thing that really choked Tycho Brahe. Kepler found that if you took the period of any planet in the solar system, squared it, and then divided it by its orbital radius cubed, you got the same number. Whether you used Earth's data, Jupiter's data, Saturn's data, you always got the same number. And after he had his fallout with Tycho Brahe, he named that number Kepler's constant. I mean, yeah, twist that knife just a little deeper. Okay? So, this is actually what's been used to help predict where planets would be in their orbits. Okay? Like when we didn't know about the existence of Uranus and Neptune, okay? This was used to help discover them. Right? We figured there must be something at this distance, okay, based on what it was doing to the orbits of other planets. So if we can predict its radius, we can kind of predict where it would be because we could calculate its orbital period using Kepler's constant. Okay? And that would allow us to point our telescopes in the right direction and discover a planet that isn't visible to the naked eye. Okay? That is exactly how Uranus and Neptune and Pluto were discovered. Okay, so Kepler's constant, okay, we're not ever going to do any math with Kepler's law of periods here, okay, but it basically says the period of planet A squared divided by the radius of planet A cubed is equal to the period of planet B squared divided by the radius of planet B cubed, okay, or these would come out to Kepler's constant. Okay? And that is true for any bodies orbiting the same central body. So every satellite orbiting Earth has the same Kepler constant. Okay? Whether they're, the International Space Station, a TV satellite, or the Moon, they all have the same Kepler constant because they all orbit the Earth. All of Jupiter's moons, okay, have the same Kepler constant because they all orbit Jupiter. Making some sense? Okay. So all you really need to know here are Kepler's three laws. Okay, so I would write those down with their names. So that highlighted section with their names. It's a good multiple choice question. Which of the following is not one of Kepler's laws? Okay, A, B, C, or D. Okay, so just another term here that is kind of a need to know term for you guys, okay, is the term astronomical unit. Okay, we use the term astronomical unit. We're talking about the distance between the center of the sun and the center of the Earth. Okay, that is one astronomical unit. Okay, and one astronomical unit is 1.50 times 10 to the 11 meters. I got that right. Okay, so the average distance between the Earth and the Sun, okay, is one astronomical unit. Okay, so to give you an idea here, Neptune is 30.1 astronomical units from the Sun. That means it is 30 times further away than Earth. Right? Which is, of course, why it takes hundreds of years for it to go around the sun just one time. All right. Okay, so this is how a calculation using Kepler's law of periods, not one you're going to be asked to do, okay? But if you were asked to do one, this is kind of what it would look like, okay? Mars has an orbital radius of 1.52 astronomical units, okay? That means it's 1.5 times roughly further away from the Earth, or from the Sun, than Earth is, okay? So if I wanted to calculate the orbital period of Mars, so how long is a year on Mars, I could use Kepler's law of periods like this. The period of the Earth squared, okay, divided by the radius of Earth's orbit cubed is equal to the period of Mars squared divided by the radius of Mars's orbit cubed. Okay, I know 3 out of the 4 of those numbers because the period of Earth's orbit is 1 year. Okay, and the radius of Earth's orbit is 1 astronomical unit. Okay, actually I'm not bound by units here. I can use any units I want. Seconds and meters, years and astronomical units, whatever. Okay, so I just want to figure out how long is a year on Mars. So to isolate that number, I would simply multiply the radius of Mars's orbit cubed, which they gave me, okay, over to this side, and then I would square root everything. Okay, now this looks like it's a complex calculation, but when you punch in the numbers, the radius of Mars's orbit is 1.52 astronomical units. So I cube that number. Okay, and I multiply it by the period of Earth's orbit, 1 squared. And then I divide it by the radius of Earth's orbit, cubed, 1. Okay, ends up being a pretty easy calculation. I just take the square root of 1.52 cubed. Okay, so a year on Mars is 1.87 Earth years. So you'd get a birthday party about half as often. Okay. So not a hard formula to use. We don't use it very often. Okay, but that's how Kepler's law of periods works. Okay, pretty simple calculation. All right, I'm going to give you guys about a 4-minute break here, and then we're going to talk about gravitation. Okay, so you can have a 4-minute break within the classroom here, and then we'll talk gravitation. Okay, so as we said, the key here to the second part of this unit is gravitation, or the force of gravity. Okay, now, up until now, we've always just treated the force of gravity like it's this. It's just mass times the acceleration due to gravity, which is fine, provided you're standing on the Earth's surface, where g is 9.81. What if I'm out in space? What's g then? Well, actually, it's almost never exactly 0. We would assume it's like 0 because it would be really, really small. Okay? But if I'm in low Earth orbit, where the International Space Station is, believe it or not, it's like 8 something. Okay? I mean, if it wasn't, what would the International Space Station do? It would fly off. It's because of gravity that it stays in orbit, as all satellites. Same with the moon. Okay? If it wasn't for the force of gravity, the moon would fly off as well. Okay? So there is always a g, okay, no matter where you are. And it could be in reference to something other than the Earth. Right? When we get close to the moon, we don't worry about the gravitational acceleration due to the Earth because it becomes almost nil because we're way more attracted to the moon. Okay? Now, it's at this point where you want to be thankful you're not in Mr. Dickey's Physics 20 class. Okay? Because when he teaches this lesson, he starts out by making you say this. He says, look at the person next to you, deep into their eyes, and say, I'm attracted to you. Okay? Which is really, really awkward, okay, for people. Okay? It's also true, not in the sense that makes it awkward, okay, but gravitationally speaking. Okay? According to Newton, this is what Newton's whole apple story was about, okay, is that objects that have mass exert gravitational force on each other. It's hard to prove that in the Earth's environment because everything's attracted to what? The Earth. Okay? I don't notice a gravitational attraction between me and somebody else in this room because it's so incredibly puny that it's undetectable. Right? The Earth completely overwhelms that because of the Earth's what? Why does the Earth have so much gravity? Its mass. Okay? The Earth is incredibly massive. Okay? The Earth's mass is 5.98 times 10 to the 24 kilograms. Okay? That is enormous. Right? Now, when you compare it to other things like the sun, I mean, it pales in comparison. This is the mass of the sun. Okay? It's like 1,000,000 times more massive. Right? It's kind of why everything in the solar system orbits it. Okay? Now, why does the moon orbit the Earth if the sun is so much more massive? Why doesn't the moon orbit the sun? It's closer. Yeah. The two things that affect the gravitational attraction between two objects are the masses themselves and how close they are. Okay? Newton knew this. He couldn't actually do experiments to prove it, okay? Because the Earth's gravity always got in the way. That was kind of the apple story. Okay? The apple hit me in the head because I got between it and the thing it was attracted to. Okay? The apple has mass, the Earth has mass, and they're attracted to each other. That's the part that was harder for people to get their head around. They're attracted to each other, not the apple attracted to the Earth. Okay? It looks that way because the apple is so much smaller. But they are actually equally attracted to each other. We just don't perceive or can even measure the attraction rate of the Earth. Okay? But they are equally attracted to each other. It's easier to get our heads around that if we're talking about two small masses separated, okay, from each other, okay, that would be, you know, gravitationally attracted to each other. It was just impossible for Newton to figure out an experiment where he could prove that. It took a different person to come along with that experiment. Okay, so there's actually somebody out there who figured out something Newton couldn't figure out. And that was how to run an experiment where he could show that two masses were gravitationally attracted to each other without the Earth's gravity interfering. Okay? That guy's name was Cavendish. Okay? I'm going to show you a simple replication of his experiment here. Okay? So what Cavendish did is he set up four masses, four bodies. Okay? And he had them hanging from a torsion fiber. Okay, so a torsion fiber, okay, is basically just a wire. And because he knew the tensile strength of that fiber, he could calculate how much force would be needed to twist it, okay, a certain number of degrees. So what he did was he set up, I think I have a picture of it here. Something like this. Obviously, he didn't have a laser. This is a modern take on his experiment. Okay, but he had two big lead spheres, so big masses, okay, and two smaller ones. They would have been made of like pith, which would have a consistency like cork, okay, lightweight, very small, okay. And he put them like this. So the lead spheres were just on a stand, okay, so they weren't going to move, and the two smaller pith spheres were on this torsion fiber. Now, what would happen is that the masses would twist and they would move towards the big lead spheres because there was gravitational attraction between the masses. Because that attraction was perpendicular to gravity, gravity didn't interfere with it. Okay? So he could actually measure, because of how much this thing twisted, the gravitational force between those two objects. That was something Newton could never do without the Earth getting in the way. That's why, even though Newton came up with this law, this is credited to Newton. Big G times M1 times M2 over R squared. This is how we calculate gravitational attractive force. Okay? It's based on the two masses, the separation distance, that's R, and big G. Okay? Big G is on your formula sheet. This is the universal gravitational constant. This is the thing Newton couldn't get. He knew that this relationship was true, but he did not have that number. It was Cavendish who was able to calculate that number based on his experiment. Okay? Something Newton could never do because apples only fall towards the Earth. Okay? They don't fall towards other objects. Okay? So he was never able to make it work. All right, so I'm going to show you this video. And it's boring. It's bowling balls attracted to each other. Okay, but it's still like a valid kind of demonstration of this idea. Okay? If we're looking at this formula here, we know that the force of gravity is dependent on these two things, which don't change, but this does. The closer together they get, the smaller r becomes. Agreed? And if r gets smaller, fg gets bigger, which means the rate of gravitational acceleration would also get bigger the closer together they get. Okay? So it's Cavendish's experiment, okay, but it was basically the proof that was required for Newton's formula to work. Newton couldn't make that formula work because according to his calculations, without big G, everything should cross each other. Okay? Because the gravitational forces between even small objects would be enormous. Okay? I mean, if you look at the value for G, okay, it is 6.67 times 10 to the minus 11 newtons per kilogram squared meters or something like that. Okay? Like it's got crazy units, but it's an incredibly small number. Okay? That's what makes kind of classical mechanics as we know it work. Okay, so let's go back here a little ways. All right, so for an object to have weight, okay, it has to interact with another object. If I put an object out in the far reaches of space, it would effectively be weightless. Okay, if it was really, really far from any other masses, it would be effectively weightless because it wouldn't be attracted to anything. Okay, everything else would be too far away. Okay, so if we're looking at how much you're attracted to the Earth at various places, okay, we find that that number changes. Right? If you're at sea level, at the equator, you would weigh, if you were 70 kilograms, 684.6 newtons. But if you go to the North Pole, you're heavier. 4 newtons heavier. Are you bigger or are you just heavier? You're just heavier. There's the same amount of you there. So if this is our formula, M1, M2, so this would be the Earth, this would be U, okay, over R squared. If this number got bigger and these two numbers stay the same, what's different between the equator and the North Pole? What do you think? Which one? What number got bigger? Or smaller, actually, not bigger, smaller. What number got smaller? R. The Earth isn't a perfect sphere. It's not flat. That's crazy, okay? But it's also not perfectly round. It's squished a little bit, okay? And that's because of how it formed. When it was molten and spinning really fast, there was like angular momentum there that made the equator stretch out a little more than the poles where it was hardly moving. Okay? So most planets are a little squished at the poles versus at their equator. Now, you can really actually see that in pictures of Saturn. Saturn looks like visibly squished. Okay? And that's true for pretty much everything. So you weigh more at the North Pole than you weigh at the equator. Okay? If you go to Chicago, okay, which is like further north but close to sea level, okay, you still weigh more than you do at the equator. Okay, because if you're right, let's say Chicago would be probably right about here, okay, in terms of latitude, not in terms of location, it's not in Europe, okay, but it'd be about there, you'd be closer to the center of the Earth than you are at the equator, so you weigh a little bit more, okay. This is why when Olympics are held near the equator, especially if they're held at altitude, more records are broken statistically. Okay? If you hold Olympics in the northern hemisphere, okay, at low altitudes, everything is heavier. Okay? So you can't throw the javelin as far, you can't run as fast, okay? All of that stuff because everything's just a little heavier. And when we're talking about, you know, thousandths of a second or 1 centimeter for a javelin throw, it makes a difference. Okay? It's statistically more probable to break records if the Olympics are held at the equator at altitude. Okay, so if they were to hold them in like Kenya, okay, for example, okay, like somewhere like near Kilimanjaro, they would probably break a lot of records. Okay, it'd be a higher altitude near the equator. Okay, similar thing happened in Mexico City. Mexico City is obviously quite a bit closer to the equator. Okay, more records were broken in 1968 in the Mexico Olympics. One of them stood for 30 years in the long jump. Okay, the guy just came unglued. All right, is that making sense? Now, as I get further away, even into low Earth orbit, so if I'm sitting on the International Space Station, okay, I would still weigh 640 newtons. Okay? I would still feel a force pulling me towards the Earth of 647 newtons. I'm not actually weightless on the International Space Station. I'm apparently weightless. I still am attracted to the Earth. Okay? If I go to high Earth orbit, so where all our GPS satellites are, okay, and where our communication satellites are, okay, I would weigh a lot less, 15.5 newtons. Why suddenly does it drop off? R is squared, exactly. Okay, there's not a huge difference between this point, this point, this point, and that point. Okay, even out there, R doesn't change a whole lot. Okay, but once you get out to here and R makes a big change, you're dividing by a much bigger number. If you double R, you're 4 times less attracted to that object. Okay? It's inversely exponential. Okay, so that means that absence doesn't make the heart grow fonder because you get further away and you're exponentially less attracted to each other. Or something like that. I don't know. Maybe it doesn't. All right. Everybody okay with that idea? Okay. So that means that if I go to the moon, I still have a weight from the Earth. I would still be somewhat gravitationally attracted to the Earth out at that distance. Okay? I mean, that's why we have the tides, okay? And why the moon stays in orbit. If I went to the edge of the solar system, there'd still be some weight to the Earth. Not very much, so it'd be much more attracted to the sun because it would be bigger. All right, so the big thing to get here is that R has an exponential relationship, inversely exponential with FG. The further away you get, you will be exponentially less attracted to that object. Okay, masses are linear. If I double the masses, then I got twice as much force. Okay, if I cut them in half, I have half as much force. Okay, so that's the formula we were talking about there. That is the universal law of gravitation. Okay. It calculates the gravitational attractive force between 2 objects. Now, technically, if I used my mass and the mass of the Earth and then the radius of the Earth to calculate FG, should I get the same number as that formula? Like reasonably close. Should I get reasonably close? I should. Okay. I mean, the issue is that here, gravitational attraction is not 9.81. Here it's about 9.83, and maybe 9.84. Right? So even though we're at a higher altitude, we're still closer to the center of the Earth than you would be at the equator. Okay. That 9.81 is kind of an average. At the equator, it's more like 9.78, 79, something like that. Okay. All right. So if I did that, I should get about the same number for my weight in both situations. Okay. All right, everybody okay with that idea? It's not a hard formula to use. Okay. We will set it equal to centripetal force when we start talking about satellite motion. Okay, but for now we're just going to kind of deal with it on its own. Okay, so this graph here is showing you the effect of separation distance, R, on the force of gravity. Okay, what kind of a curve is this? Is that an exponential curve? It is, it's just inverse, right? An exponential curve would go up, would be the flip of that. Okay, so what we're saying there is, yes, as we get further and further away, we would see an exponential decline in the attractive force between the objects. Okay, so here's that big G. Okay, it's not a number you have to memorize because it's always on your sheet, but you'll use it enough that you'll memorize it. Okay, so 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, that's the one that Cavendish was able to calculate, okay, with his torsion balance experiment that we just saw the video of. All right, so let's try this. Let's say I want to know what the weight of something that I take with me to the moon would be when it's on the moon. Okay, I know what the weight of it would be on Earth. Okay, I can calculate that pretty easily, but I want to calculate what the weight of it would be on the moon. Okay, because if I'm bringing it back, I got to know how much thrusting force and all of that kind of stuff I'm going to need to get back off the surface and get back to Earth. Okay, so I want to calculate the weight of the melon. That's Fg. Okay, here's what I have. I have the mass of the melon. Okay, so we'll just call that mass 2. Okay, that'll be 0.65 kilograms. We also have the mass of the moon. We'll call that mass 1. Okay, and that is 7.36 times 10 to the 22 kilograms. And then if I'm standing on the moon's surface, I would have the radius of the moon. I am going to be 1.74 times 10 to the 6 meters from the center of the moon. Okay, R is the separation distance. That is center to center. Okay, it's important to know that distinction. People oftentimes confuse that, okay, with like the true radius of the Earth. It has to be the center to center distance. That's what we're talking about in this. Okay? All right, if I've got those numbers, then I should be able to calculate the weight of the melon. Okay, so I'll take big G times mass 1 times mass 2 over R squared. Okay, so that'll look like this. Fg is 6.67 times 10 to the minus 11 times 7.36. 7.36 times 10 to the 22, the mass of the moon, times 0.65, the mass of the melon, divided by 1.74, okay, times 10 to the 6 squared. What do you suppose people forget to do when they use this formula? Square the radius. Absolutely the most common mistake. Should you know right away you've forgotten to do that? Because you're going to get a ridiculously big number, okay, if you forget to square that. Okay, so punching this into your calculator, this becomes a bit of an adventure. A lot of brackets are required for a calculation like this. Okay, so I'm going to go bracket, 6.67 e negative 11, okay, and then 7.36 e 22.65, close the brackets for the top, okay, divide that by the bottom, so that is 1.74 E6, close that bracket and square it. Okay, so that melon will have a weight of 1.05 newtons on the moon. Okay, on Earth it would be about 6 times heavier. Okay, so the trickiest part of using this formula is not screwing up the data entry in your calculator. Okay? Otherwise, it's just algebra. It's a pretty easy formula to use, manipulate, but what people mess up are brackets and data entry, okay? You know, missing a bracket, screwing up an exponent, something like that. That's actually the most common mistake. Okay, questions on how that works? Okay, so obviously gravity can act as a centripetal force. We know this because the Earth orbits the Sun, the Moon orbits the Earth, okay, things like that. So we see that gravity can hold objects and make them move in a circle, right? Now, that's proven by some of the things we know from Newton, okay? We know that if there was no gravitational attraction between, let's say this is the Earth and that's the Moon, okay, that the moon would just go flying straight by the Earth in a straight line. Okay, Newton's first law. If there's no force, there's no acceleration, it just keeps moving at a constant velocity. Obviously, that's not the case. Okay, the moon does have inertia. It does want to move in a straight line. But the Earth pulls it towards itself. That would be the net force, in this case, the centripetal force. Okay? But the moon wants to go in a straight line, but it's attracted to the Earth. It wants to go in a straight line, but it's attracted to the Earth. Okay? If I keep doing that, eventually, that becomes a circle. Okay? gravity has to be acting as a centripetal force because it's causing a change in the velocity, in this case the direction, of the moon. Okay? So it can act as a centripetal force. Okay? That is the basis for satellite motion, okay? Which is what we'll go into detail on tomorrow. Okay? We'll talk a little bit about it today, but that's what we're going to go into detail tomorrow. Okay, so let's do this. Let's say gravity's acting as a centripetal force. I want to calculate how fast the moon is moving as it orbits the Earth. Okay? So I would start out with this simple understanding. The moon orbits the Earth because it's gravitationally attracted to the Earth. That gravitational attraction is making it go in a circle, so that force of gravity is the centripetal force. So Fc equals Fg. But now it's not little fg. It's not m times g. Now it's big Fg. Okay? Newton's universal law of gravitation. Okay? So what we end up with is this. Okay? Fc equals Fg. That's mv squared, okay, over r. But now that equals this. Big G times the mass of the Earth times the mass of the moon over the radius of the moon's orbit squared. Okay? Can I solve for V? Can I do the algebra that isolates V here? So I want to get V by itself. What do I do with R? Multiply it over to this side, right? So it ends up on the top. What's R squared and R going to do? Okay, so that's going to cancel out the square. It's still going to have an R on the bottom. Okay, what's this mass? There's only two masses here. Mass of the Earth, mass of the moon. Which one is that? Which one's moving in a circle? Right? When we do centripetal force questions, that's always the mass in mv squared over r that's actually going in a circle. So is that the mass of the Earth or the mass of the moon? Hudson, which one is it? Which one's going in a circle, the moon or the Earth? Moon. Yeah, so this is the mass of the moon. So that means the mass of the moon is going to cancel. Okay? How fast the moon moves has got nothing to do with its mass, only the mass of the Earth. Okay? So now I've got v squared by itself, so I just need to square root this. Okay? So what I'm left with is this. The speed of the moon is the square root of big G times the mass of the Earth over r. Okay? This is a manipulation we do all the time in satellites. Okay. All right, so when I plug in my numbers here, I'm going to have 6.67 times 10 to the minus 11 times the mass of the Earth. It's on your formula sheet, 5.98 times 10 to the 24, divided by the average Earth-Moon distance, 3.85 times 10 to the 8. I believe. Okay. Okay. The Earth is the moon, is moving at over 1 kilometer per second as it orbits the Earth. It's pretty fast. That's why if you want to land on the moon, you don't aim for the moon. You aim for where the moon will be when you get there, because it goes pretty fast. All right, that's the kind of stuff we're going to be working on tomorrow. Okay, it really doesn't get more complex than that. FC equals FG for satellites. Anytime something's orbiting something else, big FG, Newton's universal gravitational law, is mv squared over r. Okay? All right. We'll leave it there for today, guys. Hey, don't forget about the things coming due this week. Okay? You've got your centripetal force lab. That's due tomorrow. Okay? And your circular motion assignment is due on Thursday. Okay? Remember, this one's due at 8:30. I'm pretty sure I actually made it that way. Okay? But it's due at 8:30. Okay? This one here, bring to class, because that's on paper.